We're back with another episode on FML, and today we're here with Erik Von Winkle, the head of operations at DeCi Labs. They work on making science more accessible and verifiable through blockchain technologies. Eric, it's great to have you.
Thanks, Kieran. It's great to be here.
Awesome. So before we get started, can you explain a little bit about what DeSci is?
Sure. The DeSci movement as a whole is a concept that has gone back for decades at this point to a lot of original implementations of open science and how science can work to be more fair and equitable for the world around it and for the people within it. I think some of the very first implementations of what we would consider the modern decentralized science movement can be seen in some of the earliest phases of blockchain technology with projects like Gridcoin and Redcoin. But within the past year, we've seen an explosion of different projects trying to solve problems in academia, which range all the way from the beginning phases of research, so how a researcher would go about just doing reviews in the first place, all the way through to the back end of how intellectual property is stored and how funding accrues back to the scientists themselves, and pretty much everything in between. It's an exciting movement, and I'm more than thrilled to be a part of it.
So you mentioned that this started about 10, 20 years ago. Well, it was going back all the way back then. So since then, who were the largest science backers and how inefficient are their evaluation strategies for determining which projects to fund?
Right. So, governments being kind of the largest backers of science has a lot to do with the fact that science itself is and should be a public good. Taxpayers are the ones who generally fund academia. And as such, I think that there is a lot of responsibility to pick the most valuable projects out there. So it's a great question, Kieran. And I would say that governments are as efficient as can be expected at picking the best projects. I've gotten the chance to talk with quite a few different funders all around the US and around Europe over the past year, 2 years, and have been amazed with the quality of people who are there and have been kind of saddened by the quality of technology and systems that they're often forced to work with. I think as a whole, there's a lot of room for improvement in terms of academic progress and how we look at selecting the right systems of science. So one of the things that we're seeing, which there have actually been several papers kind of analyzing this, is the fact that returns on scientific innovation, as determined by a number of metrics, have been steadily decreasing over time. And you see a lot of different reasonings for that as to why this could be a thing. But one of the more prominent theories is the fact that a lot of the low-hanging fruit around individual fields have been tapped out as of recently. So a lot of the easier discoveries that can potentially be made by any given scientist in a singular field have kind of already been made. A lot of the base questions have been asked. A lot of the new knowledge that has the potential to come out is at the intersection of emerging fields. But a lot of the base technology that allows someone to find the important and interesting questions at the intersection of emerging fields is not there. Using some of the current identifier schemas, some of the current metadata schemas, it gets very difficult to accurately identify where some of those gaps and kind of hotspots in innovation can potentially be. So to kind of sum up your question, I would say it's not nearly as efficient as it can be, not nearly as efficient as it should be.
So we've seen journals have a monopoly over science for quite a while now. How are they able to maintain this monopoly?
So a lot of that comes down to the incentive structure of a scientist. So in all reality, the currency of science is a citation. It is the acknowledgement of another scientist that your work has value and that they want to build on top of it, because citations are the way that we show impact. And ultimately, the goal of science is to help push humanity forward and to provide impact in the pursuit of human progress. So journals have been able to create the metrics that allow us to track impact itself. And this is problematic. So a lot of those metrics come from Cold War era. There's something called the H index, which is an aggregation of citations of sorts. If you're curious, there's a great Wikipedia article that explains the actual calculations. But the H index is what's generally used for a scientist to determine the quality of another scientist. So the higher your H index, the better scientist you are. H index is very well correlated with the quality of journal that you publish in. And quality is, once again, a question in and of itself. But there are things that tend to be higher impact. So there has been this somewhat convoluted correlation drawn between publishing in what is known as a high impact journal and citations. The more citations you get, the more funding that your lab gets, the more grad students you get, promotions, tenure, it all comes from citations themselves. So generally, publishing houses tend to keep their monopoly by monopolizing the concept of prestige and impact, by helping scientists or by controlling the careers of scientists as they move through a given field.
We've seen in the past there's a lot of evidence of citation collusion in the scientific community. Not too present, but typically in the higher end journals, you'll see a lot of this happening. How exactly did this get started, and what do you see as a possible solution?
I mean, so the concept of citation collusion would basically be where you have a close group of scientists across different communities who will all just constantly cite each other's work. So since citations are the currency of academia, by having your small posse of people who will constantly feed you citations, you advance your career, they advance their career, so on and so forth. But this typically does lead to problems, as it can be inflated citation counts. And to a certain extent, as these posses move further and further in their career, it can actually impact funding in a huge way. So one great example of how not only this citation collusion, how rigged citations have impacted academia, but how funding itself through collusion has impacted academia comes in the form of Alzheimer's research. So there have been quite a few different papers that have been published around a small consortium of individuals in the field of Alzheimer's research who have basically controlled the entirety of funding for that specific field and have used control and influence to push their own theories. It's something called the amyloid beta hypothesis. It was recently something that came out as a study, a foundational study in the field of Alzheimer's that did not replicate. So they were able to help shape the way that funding flowed in a given ecosystem due to a lack of transparency and the title of experts to make sure that their paper was the foundation for future research and that they continue to accrue more citations and more funding. How do we address citation collusion? So it's a very interesting problem. And I think it's one that affects not only science, but humanity as a whole. Collusion is a natural human instinct. And to a certain extent, there's a very fine line between collusion and cooperation. So it's a difficult question to answer. But I think the first step in any problem, first off, is acknowledging that it's a thing. And second is just trying to gather information. I think that's a step that we need to be aware of and we need to look at. So the way that we could potentially gather information around citation collusion is by having a machine readable scientific record, which is something that a group called the Go Fair Foundation really preaches and really tries to push forward. So the Go Fair Foundation is now the standard for data sharing at the NIH. They're working closely with the NSF. I think the European Open Science Cloud, which is a, if not multi-billion, at least single-billion-dollar initiative coming out of the European Commission, uses a lot of their principles as the absolute foundation for what data sharing should be. Their goal is to try and create a scientific record which both humans and machines can navigate. So identifying collusion comes dangerously close to identifying truth. And identifying truth is not necessarily something that's possible, because, or at least not something that's easy to do. It is, if you think about Galileo as a scientist, he came in and one day said, okay, the earth revolves around the sun. The sun doesn't revolve around the earth. And everyone said, okay, you're a heretic. That's a lie. We know that that's a lie. That's definitely not a thing. Well, it turns out he was right. But the difference between truth and, I guess, or the difference between a falsehood and a controversial statement can be a very difficult thing to measure. So with this machine readable knowledge graph, what we can eventually make it to as a scientific community is the ability to identify points of tension, where something is either an incredible sensational statement, an incredible sensational truth, or a lie. And then it's up to us as a community to figure that out. So I would say that that machine readable scientific record plays a huge part, takes us 90% of the way there, where we can identify potential points that need additional information. Then beyond that, I think the idea of identifying truth and collusion is going to be a very hot topic in the near future, especially with the rise of artificial intelligence and a lot of the pseudoscience that has the potential to come out of ChatGPT in the near future. That is going to be a very hot topic. So I think the last 10% comes from decentralized social networks and attestation workflows that can help people say, yes, Kieran is telling the truth. He actually does do a podcast. Or no, Kieran is lying. He is not an Olympian. Well, I'm assuming you're not an Olympian. I don't know. Maybe you
Yep.
are. But if I say it, that's one thing. If 100 people say, yes, Kieran has a podcast, then we have a more reasonable level of trust as to you actually having that. Then the other huge aspect of identifying truth and collusion is provenance and making sure that we're working through data provenance. So I've gone off on a truth tangent, but bringing things back to collusion itself, one of the things that we need to really think about is how data provenance impacts collusion. So if I can see that I've been working with Kieran, day in and day out for the past 20 years, and every paper that Kieran writes, I cite, and every paper that I write, Kieran cites, now we have a history to go off of. Now it's not just the knowledge graph itself, but it's the knowledge graph and supporting histories. We've shifted from the version of record to the record of versions, and that kind of provenance has a lot of impact as well. But ultimately, to sum all this up, there is no perfect way to identify collusion, but we can identify friction points in the scientific record and try to use community dynamics to determine what is the best path forward.
So, with the current friction points that you just mentioned, I'm sure there must be plenty of famous examples of rejections from the scientific community. Are there any that come to mind?
So what do you mean by journal rejections? Are you thinking about issues of paper not replicating, issues of different scientific studies being rejected by the editor? Can you elaborate a little more?
Yeah, so whether it's like initial rejections from the editors where they say they don't give much evidence on why exactly a specific paper is being rejected, and then later in the years it gets published and it ends up being super important to the scientific community.
Yeah, I mean, I was actually at a talk yesterday where someone mentioned a very similar concept and work that they had done. So this was back in 2006. I don't know that this is the most famous example, but it's the one that's top of mind. There was a group in the Netherlands that did text mining on basically the entirety of bio papers. I think they took somewhere in the neighborhood of like 20 million different papers, ran text mining algorithms on top of them back when data and compute was significantly more expensive, and used that to draw conclusions about gene and disease connections, correlations, I suppose. So this group was able to backtrack human knowledge and identify points where, first off, the original paper saying that this specific gene and this specific disease are tied together when a researcher said that. And then they were able to find instances where that gene and that disease were referenced in the same paper or were put in the same sentence. And the frequency of these two things coming together correlates in a huge way with scientific literature itself. So what ultimately they were able to find is, as you go out of this graph, a machine can easily recognize this pattern 18 months beforehand, whereas a human will take significantly longer to publish that first paper. So they ended up doing a full analysis of, I think it was, I don't remember if they actually had bioRxiv. They did a very large text scraping analysis of papers and ultimately came up with 180 different correlations that could potentially turn into something. And they were rejected by the editor. Because, first off, there was too much potential for false positives. And secondarily, their sample size wasn't large enough. So they went back, they redid it, they talked about some of the impacts of false positives, and eventually this paper was published and they were right the full way through. But having to go through that, by the time they actually published the paper and made it through the bureaucratic process, a good number of the problems that had originally been identified in the paper had already come out, and the paper itself wasn't necessarily impactful. So I think that there are quite a few problems with the bureaucracy of scientific research and with just in general the process of publishing itself. And this goes very strongly into peer review.
That actually sums up exactly what I was looking for. So you said that machine learning systems in the future would be the best way to approach science in general. What exactly would these next steps of creating a machine learning system look like? What would we require in order to create that system?
Yeah, so I think a lot of the machine learning systems have to come from interoperable data. So if you think about the general concept of open science, there are quite a few different sub-movements underneath that. You've got open access, you've got open data, you've got open hardware, you've got open educational resources. And at this point, the scientific community has fought the good fight around open access, to say the least. The next frontier on that one is open data, more than likely. So if we can work to make scientific data interoperable, to change the incentives around sharing scientific data, we can start to make some pretty huge steps. So a machine-readable scientific record is what enables some of these larger machine learning algorithms to have the information that they need to work. And it consists of kind of two main things: the persistent identifiers that link information together, and the metadata that describes the information, so that as a machine is sitting there and crawling through the entirety of science, it doesn't have to go into every single file and try and guess what's actually there. There's a clearly formatted metadata component on any given file, which is persistent, which is going to be in the place where it said it was going to be at any given time. And that's where the persistent identifier comes into place. And then you have this identifier, you have this metadata, then you've got the actual data underneath. The data itself can be anything. It doesn't even necessarily matter as long as it's described accurately. So I think as we move towards machine actionability, those are kind of the key points there. But one of the things that I mentioned a little bit earlier as I was talking was shifting the incentives. And this goes back to some of our conversation around the H index, where as a scientist, data is really expensive to make. It's expensive to store. It's expensive to run compute. And ultimately, if you can get the funding for that, that's a competitive edge in your career. Any large data set can be viewed as its own little gold mine, right? It's natural resources that you and your lab can continue to tap into and mine citations out of for the next decade. And it makes life a lot easier. But ultimately, by the time that you're done mining that data, technology has progressed to the point where that data isn't necessarily useful to anyone. So either you can get twice as many citations, or the world can get 4 times as much progress from that data. And I have very generalized metrics, but you get where I'm going with that. Making sure that citations are not the only measure of impact, and that there is a reasonable boost to someone's career for sharing data is going to be a huge part of a machine actionable scientific record, because that is the ground floor, is people actually entering the data, people entering the metadata and deciding to make it open in the first place. So that would kind of be the answer I would give on that one.
So, what other metrics could be used in addition to citations for science research?
You know, I can give you a couple off the top of my head, but I'm going to start this out by saying that's not for me to decide. I think what ultimately matters is that we have open data, open metadata, and quality persistent identifiers so that anyone who wants to make a metric can make a metric. And ultimately, it could be the number of times that your code has been queried. It could be the amount of compute resources run on top of your data as compute is co-located with your data. It could be the number of data pulls. I think citations will still have a large part to play. It could be attestations. There could be some kind of monetizable super citation that someone decides to throw in. I don't know. There are a million different possibilities, but the thing is, it shouldn't be for large monopolies deciding what that citation is. It should be something that's open for any and everyone to work on. And another thing to kind of mention with that, the concept of quality in computer science is going to be very different than the concept of quality in biology. 2 completely different fields with completely different like working and incentive structures, and ultimately you need a certain level of flexibility to make sure that all of those different fields are accounted for appropriately. So I think it's a decentralized plurality of metrics that ends up being what shapes the direction of scientific progress.
So, what exactly is DeSci Labs working on to create a more accessible platform for scientists?
Right. So it's a couple things. And first off, I'll say it's not just scientists, it's everyone. It's open source developers, it's scientists, it's the general public if they so choose to look. So the most important thing to us is learning from some of the mistakes of the past. So if you think about open science as this larger umbrella movement, with us having fought the good fight on open access and unfortunately still fighting that at the moment, open data is likely going to be the next frontier, right? And the people who are positioned well to handle and host scientific data are, unfortunately, a large oligopoly of private companies. You got it. It's the Amazons and the Microsofts and the Googles who can immediately scale up to a petabyte on a moment's notice. But what happens with Amazon is you put your data into a silo where if Amazon decides to cut the switch or to continue raising fees, they have the complete ability to do so. And it is well within their rights. The most important thing is building an architecture that is resistant to vendor lock in so that on a decentralized network, people can access data, people can rely and trust data. It is separating the data and the application layers such that there is no incentive to monopolize information itself. And that's a very, very tricky thing to do. So part of what DeSci Labs is doing, first and foremost, is building on top of decentralized web technologies, using concepts like IPFS and content address storage on the Filecoin network to make sure that 6 different copies of the data can be stored across 5 different continents. And that not only are people incentivized for storing the data, but they're incentivized for accurately retrieving the data and for retrieving the data faster than anyone else. So it's using a lot of the decentralized web building blocks that are there. And then secondarily, I would say that there's a big aspect in that question around provenance. So first off, it's what are we doing to make sure that the data can be open access? But second, what are we doing to make sure that it can be trusted in decentralized networks? And a huge part of that comes down to a lot of the different PID structures and content address storage. So the idea of content address storage, for anyone who isn't aware, is that instead of having a traditional file path of where you want to go to find a piece of information, the larger piece of information itself is hashed. So it is combined into a single, I think, 256 character string that can then be the reference for the information itself. So by using that, what ends up happening is whenever someone wants to call a piece of data, they send an open call to the network saying, hey, does anyone have this specific hash? And in order for someone to return that hash, it has to be accurate. It has to be the same information that was hashed in the first place. Because if you change one single bit on that hash or on that data, all of a sudden the entire hash doesn't work. So it's kind of this, it's a mix of decentralized web technologies, both from the technical standpoint and from the more human and incentive standpoint, that can bring us a little bit closer to a truly decentralized web for science, an internet of fair data and services.
So currently, what are the biggest hurdles to approaching a decentralized science system?
Um, that's very, it's an interesting question. And I think it depends on which way you look at it. But I would say ultimately it's culture and norms. And it's been interesting diving into the culture of academia. So I'll say I've always been a supporter of open access. I've always been someone, growing up as a kid, I wanted to get a PhD, but I was advised by friends and family not to do it based on concepts like publish or perish, unpaid grad student, all of these different problems that are surfacing day in and day out. But it's, I think from a cultural standpoint, the way that an academic thinks is on a time horizon of decades and decades, right? If you publish a piece of knowledge, the goal is for that knowledge to stand the test of time and to be a fundamental truth about the universe. The way that we think about progress in the scope of emerging technology is based on GitHub pushes. You need to be pushing something to the repo every single day. It's agile, iterative development. It's an understanding that perfection the first time isn't possible and that that's okay. You'll get there. Those cultural differences are something that I think we're going to see surface more and more and will be an impediment to progress. Because for starters, it's a need for open source developers to truly understand the users that they're working with and working for, and the way that they think about the world. And then secondarily, it's the need for academics to understand that things can be different in digital science, given the fact that we can cheaply and easily store information. It needed to be perfect the very first time because as you were using a printing press, you weren't going to get a second version out there, right? It wasn't
Yeah.
going to be easily circulated if you needed to make a retraction. But at this point, we have things like the Git primitive, which can make versionability almost without a user having to think about it in the first place, where mistakes can be easily corrected and can be sent through an entire architecture as fast as they're corrected. So I think that cultural aspect is going to be a huge part of friction. And then also a lot of the prestige mindset, a lot of the silverback incumbents who are served well by the current system, because ultimately it's early career scientists who are punished the most by the current incentive systems of science. For those who've already gotten tenure and who have an H index of 50 plus, the system works pretty well. It's exactly what you want it to be. So I think kind of working through some of those political and power structures is going to be a huge challenge. But it's something where there is a need. There is a dedicated user base who wants to see change, who has fought banging their head against the wall for the open access movement for the past 20 years. It's the fact that things like the Nelson memo have come out, which mandate open access and came pretty close to mandating open data as well, where you see grassroots movements like meta-science working from the bottom and policy efforts coming from the White House and the European Commission coming from the top, where there actually is hope for something to meet in the middle if we can help figure out what the middle point is and what directions need to be taken to get there. So that would be my answer on that one.
That was amazing. So the second part of that is obviously funding. And as per the NIH, typically they're one of the largest funders, at least here in America. And what you typically see is the scientists they back, they generally have to be 45 years or older. And that doesn't seem like a very great metric or one of the primary metrics to determine whether the science research would be worth funding.
Mm-hmm.
So, what do you see as an alternative to the current system in order to determine what projects to fund?
Yeah, so I mean, and this is my personal take. I know a lot of others may disagree. Um, the current systems of science have problems, but it's not a fault of the people who are in the current systems of science. So I've always found that publisher bashing and funder bashing and all this kind of stuff, it tends to run rampant to a certain extent. I think a lot of the problems come from the fact that people don't have the right tools and workflows needed to do things efficiently in the digital age. I think a lot of the problem comes from the infrastructure itself not being updated. And I'll explain what I mean on that. So, as a funder in the US, normally the way that you would find early career researchers was by going to conferences, we'll say 5, 10 years ago, right? There's 2, 3 conferences in your field that are absolutely huge. Every academic flies out there. You get to see hundreds and hundreds, if not thousands, of different posters, talk to so many people, and grow your network as a funder. Because ultimately, funding agencies, they're just made up of people. Then COVID hit, and these conferences went by the wayside, as they should. And as that happened, well, a funder still has to allocate money. They still have to show returns to the taxpayer on the investments that they made. And if you don't spend your money, as with any good government, your budget gets slashed. So you're going to spend the money, right? Given that they didn't have ways to go out and find younger researchers, given that there was no transparency, that there was no good infrastructure for finding early career researchers, they continued allocating money towards people who were older. I think that's just one example of how a lack of transparency leads to bubbles and stagnant networks. I think one of the best things that we can do is try and help the current workflows, help funding agencies gain more transparency, gain a better line of sight into the growth of a given field. If a funder can look at a massive knowledge graph of their field and identify a tension point and see, hey, this tension point came from a 25-year-old. Hey, I'm going to get a couple people to look at that. Oh, it replicates. That's awesome. Now I've got a person who I want to fund. Now I've got a way to reach out and contact them. I know exactly who I'm looking for, who I need to get in touch with, and can start to build that rapport with them, that human to human connection. I think ultimately that's probably where we need to go.
So you mentioned something about replication in research, and that has come up quite a bit. We're going through somewhat of a replication crisis right about now, and a big problem is creating research that isn't replicable because a lot of these journals, when you replicate research, it's harder to get published. So there's not much effort being put into these replications. How exactly would we even begin to solve a problem so great as the replication crisis?
Oh man, I'm loving these questions. Yeah, it's a tricky one. And this is one where I'm going to start with a non committal answer of saying that there is no perfect solution. So, for those who may not be aware, the replication crisis is a phenomenon in academia where scientific papers cannot be repeatedly remade. So, there are two different concepts within this: there's reproducibility and there's replicability. Now, if you as a scientist have created a piece of truth, a fundamental truth about the universe, and you publish a 30-page paper that describes what your hypothesis was, how you tested it, and what the outcomes were, well, someone 10 years later on the other side of the world should be able to take that middle section of how you did it and completely reproduce the results. That's called replication. Reproducibility is just where someone can link your code and data together. They're not recreating your entire experiment. They're just clicking the run button and coming to the same graph. Now, it's coined the replication crisis because I think in some examples, like for instance, cancer studies, as many as 90% of papers do not replicate whenever people have tried to replicate them. But there are also some very serious issues around just the bare minimum of reproducibility. So to go into how do we fix the replication crisis? Well, it starts off with culture, right? We as a scientific community need to build a culture where replication itself is celebrated, where it is rewarded. And one of the more interesting avenues that I've heard is around the concepts of replication grants. So if you're, let's say, a large pharmaceutical company and you're thinking about building out a new drug, you're going to stand up a multi-million-dollar R&D team. You're going to do your testing. You're going to get all the admin work done around it. You're going to build the labs. It's going to be an incredible amount of money. If you could just put $100,000 down at the beginning to get a different group of scientists to go back through and retry that study beforehand, that would be a pretty good financial bet for you. That infrastructure does not exist right now. So I think ultimately parts of that come down to money. Parts of it come down to just pure reproducibility and provenance. So you may not need the same emphasis on replication if there's general transparency in the systems of science. If someone can see your code, if they can see your data, and if they can understand the steps that you took to get to where you were, they may be more understanding if your paper doesn't replicate. It may not necessarily be a crisis, it may just be a singular mistake. Um, and then finally, I mean, there's something called the natural rate of non-replication. If you're performing, let's say, a study on social sciences, something around psychology in China 10 years ago, and then someone else were to try and recreate that study in the US 10 years from now, it's probably not going to replicate. Those are completely different cultures, completely different time frames. Things have changed. It's okay that some things don't replicate. That's not necessarily a problem. But it's making sure that we celebrate the things that do, that we provide incentive structures for replication, and that we make reproducibility, so not replicability, but reproducibility, an absolute expectation. I think that would be a huge part of the answer. There's several other I can give at this point, but it's a good stopping point.
So just to end off, there's one big question related to replication I wanted to ask regarding what exactly would a solid replication system look like, or what are the steps required in order to get to a incentive model that would work with the scientific community for promoting replication or reproducibility?
Oh man, that's a very, very difficult question. And ultimately, I think it depends field by field. Um, I think one of the best things that we can do to work towards that is supporting the meta science movement. So, for those who may not be familiar with the concept of meta science, this replication crisis that I just mentioned got bad enough that what can kind of loosely be coined as a grassroots vigilante movement in science had to spin up to continue checking the work of others. So it was a group of scientists who would go around and with no incentive at all whatsoever, in fact, it probably hurt their career more than it helped, would go around and try to remake the experiment of others, right? So that has gone from this grassroots movement into a legitimate field of science where we are using the scientific method to study science itself. If we want to talk about the most impact that research itself can have, I think meta-science is one of the best fields that we can focus on. Because ultimately, Kieran, I can't give you all of the answers on this podcast, but I can tell you the people who can, and I can help provide the right direction for eventually moving towards those answers as a larger community. I think supporting meta science research, moving towards a machine actionable scientific record, and moving towards open access, open data, and general provenance.
Okay, so if anyone wants to follow the work of DSci Labs, where exactly can they go?
Yeah, so I would say the best point of entry is our website, and that's desci.com, DESCI.com. From there, you can find links to a lot of the different stuff that we do, including our first product, DSci Nodes, which is the front end interface to this scientific record that I've been talking about. If you go on and you play around with it, please, by all means, use the feedback button on the bottom right-hand corner as much as you would like. We appreciate any and all feedback. Then from our website, you can navigate to our Discord, which is a community of over 1,000 people at this point that are interested and passionate about using emerging technology, specifically blockchain and AI, to try and help meta science efforts. So if you want to come join that, we would love to have you. Just introduce yourself and we'll go from there. Then I think we've got one other large program that we're running at the moment. It's called Node Stewards. And the idea is that we as a community have to help spread the word around some of the possibilities of fair data and open access. So for anyone that's interested, we're building out reproducible research objects, which you can see a couple examples of that on our website, but it's a great way to help spread the word around the need for reproducibility and the need for publicity on the replication crisis. If you're interested in helping build out some of those first example stellar research objects, we'd love to have you. We would appreciate the help. Come in and introduce yourself and mention an interest in getting involved with that specific effort.
Perfect. Eric, it was great having you on the podcast today.
Absolutely, Karen. It was a pleasure to be here, and thanks for having me.